Great. So, all right. So as I was saying, these two lectures are meant to describe applications of NMR to nucleic acids, but because nucleic acids are in many ways unique molecules, some of the most critical applications involve a technique called residual dipole coupling measurements, which I think I would like to introduce today, because it's so central to anything we do with gases, and not only my lab, but more broadly. And this will build on some of the material that we covered in previous classes, including, I think you've learned about anisotropic interactions and anisotropic tensors. So we will have a little bit of tensors, and I'm not going to go too deeply into that, but enough to hopefully make you appreciate the strength of this approach. It also nicely connects to solid state in some ways that I'll show you. In many ways, visual dipole couplings are an attempt to bring a little bit of solids and a little bit of solution state NMR together, and I'll describe that during the course of the lecture. So I'm going to be introducing RDCs quite a bit today, but I will fuse it in nucleic acids to show applications of RDCs to nucleic acids, and then tomorrow's lecture will focus on more of your generic, how do you assign a nucleic acid, and then how does one perform resonance assignment, but also some adaptation experiment. And so there's a combination of applications and also some material that involves actual methods. Okay, so residual dipole couplings are those originate from the dipole interaction in the Hamiltonian. And so I'm showing you here a bond vector in a molecule, a carbon-proton bond. And this carbon bond vector lives in a molecule somewhere. And this sample is inside a magnetic field. And the bond vector makes an angle with respect to this applied magnetic field. And the dipole interaction is governed by the equation shown here. And you've got your gyromagnetic ratios. So the bigger the gammas, the bigger the dipole interaction. It depends inversely on the distance q. So the shorter the distance, the greater the dipole interaction. And then you've got some constants. And then we have this critical angular term, which is the spherical harmonics y20, which you may have encountered already. And it's the theta cos squared theta minus 1/2, where the theta is the angle between the bond vector and the applied magnetic field. This angular bracket denotes a time average over the function, because in solution state NMR, the molecule is constantly tumbling and undergoing overall tumbling, and as a consequence, the angle is constantly changing. And over time, what one will observe is the time average, or the ensemble average of all the different orientation sample, and the dipole interaction will therefore then manifest itself as sort of the average of all the different orientations that one has under solution conditions. Now, I think this average angular term is magical in many ways. It's like a very special term. It's spherical harmonics. It's a function that I think is worth really thinking about deeply for a wide variety of NMR phenomena. Many interactions with NMR depend on because we're two, whether it's CSA or dipolar, whether it's manifestation of energies or relaxation. And so I think it's good to kind of really build the intuitive understanding of it. And so I'm going to start by, I can draw on the board, right? Oh, no, I'm not going to change. Okay, but can people see me there, right? Oh, yes, they can see the board. But they can see me. They can just change the camera, so. That's it. I will wait for your camera. No, that's it. I will draw beautifully with my hands, in the air. So, well, actually, I can ask you. So let's map out this function. What's the maximum of this function? At theta equals to. So at theta equals to 0. Cosine 0 is 1, 3 times 1 minus 1 is 2, 2 divided by 2 is 1. So the maximum is 1. And then as theta increases, what's the minimum of the function? Minus 1/2 at theta equals to 90. So it goes from plus 1, goes to passes 0, continues then to minus 1/2. And then it goes back to plus 1, minus, you keep going right away. So it's an interesting function because first it has a crossing at 0. What is that angle called? The magic angle, 54.5 degrees. That's when the dipole interaction is 0. And its maximum of plus 1, that's theta equals to 0. And the biggest negative value is only 1/2 the size of the positive. So it's asymmetric in terms of the positive and the negative. Okay. So that's, hopefully you have an image of that function in your head. So then the next question is, okay, so I would like to compute what is the average of this function for an isotropic distribution of orientations where theta has no bias. So how would we go about solving that average? How does one determine the average of a function? If I have a function f of theta, for me to solve the average of the function, what is the integrate? So integrate over the range, which will be in this case the full range, 0 to 2 But what else do you have to do besides integrating the function? What else do you have to add? Divide by. Yes, there's a normalization. But what else do I need to multiply it by? Well, don't say that yet. But what you need a distribution function. Right? So I need the distribution function. Because if I want to compute the average of a function, I need to first integrate, which is essentially to sum. An integral is nothing but a sum over a very, very narrow window of theta. So I need to compute the function for every little infinitesimal theta, right? And then add it. But I need to also know for each theta, what is the probability of that theta, right? The distribution function that I'm interested in. So therefore, the average of any given function f theta is the integral of f theta times the distribution function, let's call it d theta, over the bound 0 to 2 pi, and there's a normalization constant that you have to have. Okay, so we need a distribution function, which is to say, what is the probability of a given theta n? So if I have my vector in solution and it's randomly sampling all orientations, what is the probability of a given theta? Is one theta more probable than the other? It's a totally random distribution. My vector could be anywhere. So is there a more likely theta to form than another, or are they all equally probable?
I could know the more like probably than
Theta equals to 0. So it's more likely if I walk in a room of a random vector moving around, the most likely theta I'll see is 0. How many ways can I be 0? One way. Imagine I take literally a vector and I randomly allow it to sample a sphere of orientations. The number of ways I can get 0 is only 1, right? Which way do I have the maximum way of getting 90 degrees? I have a large number of ways I can get 90. It's very counterintuitive, by the way, because you might think it's just theta, right? And if you integrate theta up to theta minus 1 over 2, you get a very different value because you multiply it's like theta is a constant. Or if you multiply by theta, if your distribution function is just theta, but in fact it's 0 at the probability is almost 0 at 0, and it's maximum at 90. What function does that? What function is maximum at 90, but the minimum at 0? Sine theta, and that defines the arc around the sphere, which is literally what we are thinking about. So imagine I have this pen, and I can have any orientation in space. It will have many more likelihood of having a 90 than, and that's given by sine theta, which defines the length of the segment around the sphere, right? So therefore, the distribution function is sine theta. Now remember that theta squared theta is asymmetric, as we discussed. It's plus 1 on the top, and it's minus half. So if you were to do an integral, which is the area under the curve of just that function, what's the average of? Is it positive or negative or 0? If I take theta squared theta minus 1 over 2 and I integrate that from 0 to 2 pi, and what is will that be a 0 number, positive or negative? Any thoughts? Just the integral of theta squared theta minus 1 over 2. Because it starts +1 and has a huge amount of positive area, and then a very small amount of negative area, right? If it were symmetrical, like sine theta, the positive lobe and the negative lobe have similar areas that are opposing each other. So if you sum those areas, you get 0, right? So the integral of sine theta over the period of 0 to pi is 0. But theta squared theta minus 1 over 2, what do you expect the integral of that to be? Positive, right? Well, but the dipolar interaction is not observable in solution NMR. Well, guess why? Because the sine theta gives some help to the negative value being only -1/2. So even though the most negative value is only -1/2, the sine theta distribution amplifies the 90 angle because it's the most probable. So -1/2 gets help, a helping hand from the distribution function, which says, oh, by the way, -1/2 is the most likely orientation, whereas the 0 one has very small likelihood. And if you multiply the function, if you look at the function theta squared theta minus 1 times sine theta, that has positive and negative lobes of equal amplitude. So the integral of that, which is what we are interested in, is 0. You see, that's very important to appreciate, I think, because what we call isotropic distribution is actually sine theta, not just theta is any number or any value. So as a result of that, the dipolar coupling in solution is equal to 0, because thanks to rotational isotropic tumbling, one averages the interaction out. And as a consequence of that, we call ourselves solution state NMR spectroscopists, because we want to get rid of these dipolar couplings and CSA interactions because they're enormous otherwise in the solid state. And so much of the high resolution, the nature of solution NMR being high resolution arises because these interactions, the second rank anisotropic interaction. So the dipolar interaction is a second rank anisotropic interaction. They all have the same property of having this spherical minus y to 0 dependence, and they all average to 0 under isotropic distribution. By the way, that's an interesting, we live in a world where we happen to have physical interactions that average to 0 with a random distribution. And as a consequence, we can enjoy solution state NMR. What's another anisotropic interaction, which is described in anisotropic tension? The CSA. The CSA has an anisotropic. The dipolar couplings are purely anisotropic interactions. So if they average to 0, you get to see none of them. They don't manifest themselves in our spectra, in our solution state spectra in terms of energies. Energies always show up in spectra in terms of either splittings and movements of peaks, right? So energy contributions show up as changes in frequency. Since we don't have any dipolar coupling interactions in our NMR spectra, our peaks are basically just devoid of dipolar contributions. But CSA, is it a purely isotropic interaction? It's got an isotropic component and it's got an anisotropic component. So we see the isotropic chemical shift in solution NMR, but we don't see the anisotropic part of the interaction. So therefore, understanding the averaging of the dipolar interaction not only lends itself for dipolar interactions, but also the anisotropic part of the CSA tension. Okay, so now, while it's wonderful to enjoy the high resolution of solution state NMR, and of course, the solid state NMR tries to get rid of these dipolar interactions by means of rotation of the sample around the magic angle. And the way to think about that is if I have a bond vector oriented anywhere in space, if I spin it fast enough, the average orientation of the bond vector will be along the magic angle. And of course, I have to spin it faster than the dipolar interaction in Hertz to be able to create the conditions of an average Hamiltonian. But that means that all my dipolar vectors are oriented on average along the magic angle. And at the magic angle, the dipolar interaction is 0. And so you can get rid of the dipolar interactions. Now, in solution NMR, so one way is orienting along the magic angle and spin. The other way is exploit sine theta that arises from the isotropic distribution in solution state NMR. Two radically different ways of averaging to 0, actually. They're very different, right? Because one is a sine theta distribution, the other is project along the magic angle and spin. And in fact, there's some tricks you can do in solid state NMR that would have probably not been possible if you were relying on an isotropic distribution. And there's all kinds of sequences, and maybe you guys will go over that and go as coming in. Okay, so that was just one slide, but that is a big thing to appreciate. Okay, so in terms of the physical, So in terms of the physical nature, so you might wonder what, how do I build a physical understanding of the dipole interaction? And it really is no different than the interaction of magnets. And so, for example, here I have a spin eye. You see, I can use a cursor here, right? Let me see if I can get a cursor. Use a pointer. Laser pointer. Can you guys see my pointer? And you can see it too. Okay, great. So I have a spin eye and I have a bonded spin S. And now the spin S can have either its nuclear spin in the alpha state or the beta state, right? My neighbor can be either spin up or spin down. That changes the orientation of the magnetic flux emanating from that nucleus. And so in the context of spin up, I get this straight field. When it's spin down, I get the opposite straight field. Now I'm sitting here, I'm spin eye, and I'm sensing the field from the neighbor S nucleus. And let's say here I'm in an orientation which is perpendicular to the field. This is the situation where my theta is 90. So I'm going to experience the magnetic field, but also the opposition at tiny, by the way, these fields are minuscule relative to the static magnetic field, but nevertheless it's there. And so the I spin feels an opposition to the field when X is spin up, and it feels an enhancement of the field when X is spin down. And in the context of therefore their resonance frequency position, when I enhance the field, I shift to the left. When I oppose the field, I shift to the right. And so therefore, because I have a 50-50 mixture of spin up and down, theoretically, I get a splitting. Those two states have a difference in their frequencies, and the magnitude of that splitting shown here is the dipole couple. Now, remember here, I'm freezing my sample, hypothetically, in this 90-degree angle. And if I were to collect imaginary, let's say, the energies of the states, I would get the splitting, which is the dipole couple. Now, if I now bring my nucleus closer, or shorten the bond length, I get closer to the magnetic flux. A magnet, the straight field from a magnet to the magnetic field, the density of the magnetic field increases as you get closer. And so that explains the R to the power 3 dependence. That's literally describing the magnetic field's MNE. And remember how we mentioned that when you're 90, you only get a -1/2, whereas when you're 0, you get a doubling of that effect. Well, the doubling can be understood here when I have an orientation of theta equals to 0. When I'm spin eye, now I'm enjoying two lobes of the magnetic field, right? I'm getting the left and the right, so I'm getting a slightly greater enhancement. And when I'm spin down, I'm getting a slightly bigger opposition. And so the magnitude of the splitting is great, right? So that's why I get a +1. The behavior is such that you get up to a +1, but you only get down to a -0.5 when you have the behavior. So this is the physical physical sort of manifestation of that properties, and the theta cross square theta minus 1/2 angle literally describes these straight magnetic fields. And that's the functional form that describes the behavior, but that's the underlying behavior. Okay, so, and of course, in solution, by the way, the magic angle is beautifully the place where the flux is perpendicular, the magnetic flux is perpendicular to the field, right? Because in some areas it's going up, in some areas it's going down. When you're at the magic angle, if I were to put my spin over here, then the actual contribution is 0. And that's where the dipole coupling is at that. Okay, so in solution, the dipole interaction averages to 0 because of our sine theta distribution function, and dipole couplings disappear from observation. However, of course, we would love to measure dipole couplings because they depend on the orientation relative to the magnetic field. And if one were able to measure the dipole couplings for a bunch of vectors, you could say something about their orientation relative to the field and therefore relative to one another. And if I can define the orientation of you relative to me and the orientation of Yang relative to me, in many ways I'm defining your relative orientation as well. So there's angular, potentially very rich angular information included in dipole couplings, which, and of course, solid state NMR can exploit that rich information. But how would you bring back the dipole interaction in solution NMR and make it measured so that you can at least use it? What would be the approach? How would you we've got a chemical solids, you got a state solution NMR. What do you have to do to bring back dipole coupling? And I'm mostly going to ask the solid people here because I hope the solution guys know the answer. My lot, but you still know the answer. But how would you bring back under solution conditions the dipole coupling? The reason it's zero is the sine theta angle. The sine theta, the random distribution in sine theta. So how can you break that? Suppose my sample is not randomly oriented anymore. See, it's not sine theta. It's not fully randomly sampling space. What will happen? Will my average be zero? It will not be zero. Because literally zero happens with the sine theta function. And so a long-standing quest has been to introduce ways of breaking the randomness and induce partial alignment. So the idea of partially aligning your samples, not making them fully aligned with the solids, because we want to retain, we want to have our cake and eat it too. We want to retain the solution state quality of the spectrum, but we want to break the symmetry of isotropic distribution and bring back some degree of that. But the way to do that is partial alignment. So if you have a molecule and you want to partially align it in the magnet, how would you do it? What could you apply to a molecule? You have a molecule, it's got properties, it's in the test tube, it's in solution, you want to partially align it. Again, and for those of you in my lab, you think about ideas other than the answer.
Are you saying spin alignment or the?
Great question. Can I cheat the spin alignment? So suppose I put my sample in the magnetic field, where are the spins quantized? So my molecule is tumbling. Where are my spins? How are my spins aligned? You can't play. I mean, that's no matter what the orientation of your sample is, right? Your spins are always up or down. I'm not talking about that because I'm talking about the theta angle, which is the angle between the bond vector of the spins and the magnetic field. So I'm talking about the physical the molecule itself and its orientation in the solution. I would like to partially align it so that it's not tumbling, it's not sampling every orientation with equal probability. Currently, my molecule samples every orientation with equal probability, but I want to break that. How would I do it? How would I align my sample? What do I do? No, but that would be the obvious answer. Give me a more interesting answer.
Or tricky. You just make the molecule deviate from below the shape.
Okay, so if I have a molecule that is rod-like, will that rod-like molecule align, Rachel? Will a rod-like molecule align? If I just change the shape? It will? Why would it prefer, which orientation would it prefer? I have a rod-like molecule, it's in the magnet. You're saying that it will, to say it's partially aligned means that it has a preferred orientation. Why would it have a preferred orientation? It wouldn't necessarily unless there's something, right? Like there's a force that says, yeah. Love that idea, electric field. And see, I have this, you and I have discussed this before, right? Because literally the first, here we go. The first attempt to align a molecule was with the use of an electric field. So, before I go there, let me go back. With that part, I actually mentioned this slide. So what degree of alignment do we want to have? So the ultimate degree of alignment that we would like to have is something like 10 to the minus 3 to the 10 to the minus 2. What this means is that 1 in 100 molecules or 1 in 1,000 molecules are on average fully aligned. Although that's not really what we're doing, but just to give you a feeling, this is a small amount of alignment. If the alignment is smaller than that, the dipole coupling becomes too small to be measurable, because the dipole interaction, the residual will be very tiny, so it's not very helpful. By tiny, I mean smaller than the line width, so that it becomes impossible to resolve. If it's too much alignment, you get back to solid state NMR, and then you end up with many dipole coupling networks, and you're not necessarily running solid state NMR, or state solution. So it's roughly, so you need to, you don't only want, so you want to be able to modulate the amount of volume. You can't just say, I'm going to partially align it. You've got to align it and ideally have a tunable system. And so there's a huge history in NMR to try to partially align molecules to the optimal levels. Thank you for mentioning that. I think that would be the obvious, because molecules have an electric field that allows, because if it's not symmetric, obviously, that you could then rely on to partially align them using electric potential. What else could we use? What else could we do to partially align them? So this one is less obvious. So this is the history. I'm going to fly through these slides because, in the interest of time, and I will add these slides in the course tool so you guys can have access to them, and you can look at the very big long history. But I want to focus on this slide because it brings us. So there's a whole realm of trying to align organic molecules in the 60s, 70s, and 80s. And a lot of what we have in biomolecular NMR, as is usually the case, borrows from those initial applications. But here in the 90s, these applications began on biomolecules to try to partially align. And my favorite form of alignment is, it turns out that since we're talking about nucleic acids have an anisotropic magnetic susceptibility tensor. That's a big word. What do we mean by that? If I take an aromatic nucleotide base like a guanine or an adenine, it's got a bunch of electrons that circulate in a way to oppose the magnetic field. When they circulate, that creates a magnetic susceptibility, which creates a little vector you can think normal to the base. And this induced dipole, so you end up inducing a magnetic moment in the base, which is normal to the base plane. And this induced magnetic moment, little mu, is going to interact with the field. And it will, if it's a diamagnetic molecule, that interaction is unfavorable. So it will want to be oriented perpendicular. So if I have a long piece of DNA, each little base, and I'll go over this a little later, each base has a magnetic moment, if you will, that's induced by the magnetic field that is normal to the base plane. And if you have many of those little base pairs in a long piece of DNA, they collinearly add to create a very large magnetic moment. And so what happens is the magnetic field induces a magnetic moment. The magnetic moment in turn interacts with the field to create a preferential alignment, where being perpendicular is the preferred alignment and being parallel is the worst alignment. And so you end up with an energetic penalty to be parallel. So in the solution, by means of interaction between the magnetic field and the magnetic susceptibility of the DNA molecule itself, you create a slight preference to be aligned perpendicular as opposed to parallel to the magnetic field. And many don't know this, but the first application, yes.
Any comes to field at which you can just take DNA and water and see it obviously.
Say that again? Yeah, absolutely, yeah. So this was done at 600, you can do it even at 700. And I'll actually go over that. It's really cool. I'll describe that alignment mechanism. And actually, so now that I told you, the magnetic field induces the magnetic moment proportional to the magnetic susceptibility. And that moment in turn interacts with the magnetic field to create partial alignment. So magnetic alignment depends on the magnetic field to the power 1, 2, 3. Let's go through it again. The magnetic field induces the moment. The magnitude of the moment depends on the magnetic field. Once you generate the little baby moment, it interacts with the field to induce alignment. So you've got B twice, so it's B squared. So the magnitude of alignment of DNA or RNA under magnetic alignment grows quadratically with the magnetic field, which is interesting to note because not many things go quadratically. Now, the dipole coupling pair will also scale quadratically with the B squared, but the CSA, the residual chemical shift anisotropy, the other anisotropic part of the chemical shift, will scale to B to the power 3. And it's one of my favorite. If you ever want to convince somebody to buy high yields to powder, the best argument is to measure residual chemical shift anisotropies in the nucleic acids because it actually grows to the power B to the power 3. But so B to the squared means, and the earliest experiments ever done to align a molecule, measure, so because your dipole coupling is not going to be 24,350 hertz. For an NH bond, if you're a solids person, hopefully you know that number. That's like that's the magnitude. If your average angular term is 1, and you think about an NH bond with a distance of 1 angstrom, your magnitude of your RDCs is 24,000 hertz, which is enormous. But if my alignment level is 10 to the minus 3, you scale down 24,000 to 24. That's the ballpark where we want to be in solution state NMR. We want a 10 to the minus 3 scaling. But magnetic alignment is so weak, and we'll go over this in the early application. You were getting like 0.2 hertz, you know. It was a very small degree of alignment, but it was first observed by Walter and Alex in Wesleyan. And this was in a thesis that was never published. And it was measuring RBC between H5 and H6 protons. The first published example of magnetic field alignment was actually done by Prestegard in 1995, where he took another way of partially of aligning magnetically molecules is if they're paramagnetic. So you can be a diamagnetic molecule. Most of us are diamagnetic. Most molecules are diamagnetic. Most of us, but to be paramagnetic, you typically have to have a metal center. And so cyanotic myoglobin. But one can take myoglobin and basically subject it to cyanide. Very mean thing. That's how you die from cyanide. Cyanide interacts with the heme, create a paramagnetic protein. The paramagnetic susceptibility tensor tends to be, on average, 10 times bigger than the diamagnetic tensor. So you can get a boost in alignment. And they demonstrated the measurements of RDCs, residual dipole coupling. We call them residual because it's not 24,000 hertz, which is what you expect for a solid, for a bond vector that's aligned parallel to the field. But instead, what they measure like 0.2 hertz, 0.4 hertz in this magnetically aligned cyanotic myoglobin. We'll come back to, so how do we, by the way, if I put my aligned DNA or protein in, let's say, 600 megahertz, I measure the splittings. How do I extract the dipole coupling? Because, you know, I'm measuring what happens is the dipole coupling is add or subtract from the scalar column. But if I'm just doing one magnetic field, I get a splitting. I have no idea what the dipole part is because I'll be measuring the contribution from both the scalar and the dipole contribution. So how do I extract the dipole part? In the case of magnetic field alignment, I vary the field. So you measure the splitting as a function of the field. I'll show this. And then if you extrapolate to zero field, what should the dipole coupling be for a magnetically aligned sample at zero field? Should be 0. So whatever is remaining is your scalar coupling. Because your scalar coupling will have baked into it a dipole contribution. So it's important to think about, you can't just align your sample, you better have a reference, which is the sample where it's not aligned, right? And if you're magnetically aligning the sample, the only way you have to avoid it being aligned is to change the magnetic, or have paramagnetic metal versus no paramagnetic metal. Like if I take a paramagnetic metal out of myoglobin and I use carbon monoxide myoglobin, which is a diamagnetic form of myoglobin, then I could subtract those two, right, and get the RDC from there. Okay, but the breakthrough happened. And by the way, I should say that I was this super dramatic. I was a PhD student when these technologies were being developed. So the 95 paper from Jim Prestegard came out when I joined the lab, and all of us knew that somehow IBATs had achieved a way of aligning any sample. Didn't have to be paramagnetic, didn't have to be diamagnetic, just any molecule you wish, they could get RDC. And not only that, they could amplify the alignment tenfold and get the beautiful sweet spot of 20 hertz RDC. So we never knew. Nobody knew what method they used. In fact, they were showing the results, showing the beautiful splitting without telling us how they did it. And I'll tell you how they did it in a second, but this really opened the way to broadly aligning molecules using what's called aligning media. Okay, so what are aligning media? So the other maybe less obvious way to align a sample is to embed it into a sample, to include in your sample an ordering medium. It's a molecule that's going to end up aligning spontaneously in the magnetic field. So some of you may be aware of bicels shown here. So bicels are lipid bilayers that spontaneously align at the right conditions, typically at high temperatures. And so why are those molecules aligning with the magnetic field? What causes them to? Why would this bicell align all of a sudden? And by the way, the normal to the coin is perpendicular to the field. What's the physical phenomena that causes their alignment? Why would bicells align? So you think it's electrical charge. But am I applying electrical potential in the sample? I have a magnetic field. But I don't really, I mean, you could apply it, that would go back to the electrical approaches. So no, it's not electrical. What makes them align? Because remember, you have a magnetic field, they know. If you were to go and have a conversation with the aligned bicep and say, hey bicep, how are you doing? I'm doing good, how are you? Can you tell me where the magnetic field is? Yeah. Because I can look at them and say, oh, the field is perpendicular to your normal, you know? So clearly the biceps know where the magnetic field is. So what's causing their alignment? Yeah. Absolutely, they have magnetic susceptibility. They have aromatic moieties, they have magnetic susceptibility tensor, which causes their to have a partial alignment. And then there's a liquid crystal phenomenon where they all add each other and they all like reinforce each other. But the underlying physical medium, physical interaction is again the interaction. If you have a magnetic field, it's going to interact with the magnetic anisotropy, which is inherent to the sample. You can also, for nucleic acid application, use phage, which are basically the genomes of phage have DNA coated with proteins, and these long rods will align actually parallel to the magnetic field because of the way the DNA goes around. And so it ends up aligning, the rod aligns parallel to the magnetic field. So now I am able to achieve this medium that is itself aligned. But why on earth would now putting the sample in the medium cause my sample to align? That's weird, right? I mean, just because we can understand that I can align phage or bicells in the magnetic field, why should that alignment transmit to a solute molecule that I put in the sample? I like that idea. So you're saying the solvent around the ordering medium is itself aligned, partially. And maybe if I share the solvent with the molecule, then the molecule gets transmitted like a kind of like a transfer of alignment. That's a good way of thinking about it. But let's watch this out. Okay, I'll be able to see that better. Gut temperatures a little bit. Oh, there's Walter. That's great. That's even better. Let's add this rod like that, and over here I'm sampling all orientations with equal probability, right? Now, weirdly enough, if I hit a wall as I go closer here, notice that there's some orientations that will be rejected, right? And as I get closer, more get rejected, and when I'm very close, only one is allowed, right? Now, in your NMR tube, you have a wall, right? So I'd like to inform you that all of your samples that are close to the wall are presumably partially aligned. It's just that the walls are very few in density. And so the proportion of molecules that is actually aligned is infinitesimally small. But by just simply having a wall that's aligned, if I now add biceps or add phage, I basically enrich my sample with walls. And if I have lots of walls, through simply steric interactions, if your molecule is, what would be a bad molecule that is never going to align? What property would it have? So if you have a sphere is never going to align. So that, because its shape is isotropic. But even a small deviation from isotropic shape will cause a preference for alignment. Not only that, a preference that one can calculate rigorously by simply like drawing a wall and doing this type of thing. Okay. There's another thing that can add. So that was the brilliant thing Advax and Islam did, which is to imagine that basically having lots of walls would seriously transmit the alignment. And they also took the bicell system, which, by the way, Jim Kretzinger, who really aligned by Logan, had developed to study membrane-anchored systems. The trick that Bax did was to make it possible to make very tiny bilayers. because otherwise they're usually huge, and that required changing the ratios of the lipids that make up the bicycle. And the trick was to make small dilutes. So normally the bicycles are very concentrated, so concentrated that your alignment is basically solids. The trick was to take that down to a dilute sample, because if you have too much wall, so the way you tune alignment is the amount of wall, the concentration of the ordinary medium. And you can literally titrate up or down by titrating the concentration of either the phage or the bicycle. And bicycle feed first, the phage came second. In addition, though, imagine my bilayers are negatively charged. I can dope my bilayers, by the way, with positive lipids, negative lipids. And say your protein is charged. Now you risk, depending on your perspective, now you might stick to it. You know, you're a protein, you stick, and by the mechanism you mentioned, by virtue, if you stick to me and I am aligned, you're getting aligned, right? But now you're getting worried. I can tell you're getting really restless. You're like, oh, but isn't that changing your molecule? Could it be that when you bind the bilayer? So that would be a concern. In addition, quantitatively modeling that interaction gets difficult. Like I can predict steric effects based on shape, but predicting like a charge interaction, and you can get electrical quadruples. That the electrical interactions can be quite complex, actually. And there's some work by Spectroscopy that tries to model these complex charge interaction between the medium and the solid. More in general, for nucleic acids in particular, if I ever get into nucleic acids, one likes to use phage because phage is negatively charged. Nucleic acids are negatively charged. And it turns out that you can think of negative charges as just being a steric with a thicker wall. You know, it's like they'll hit the wall before they actually hit the wall because of the charge potential. But so they're well defined by a steric wall. Now, there are many other ordering media that have been developed for this purpose of aligning molecules to get a small amount of alignment. And I'm not going to go through these. They vary in terms of their suitability across pH, temperature, their compatibility with the solvents. And there's a whole industry on developing, even to this day, new ordering media that are cheap, convenient, easy to use, part of the alignment system. And here's the typical steric model that I just described, where for some systems where they're either neutral or light charge interactions, you can very much predict the behavior of the molecule and its alignment by means of just a simple steric collision model. Okay. So let's say now I take my RNA and I partially align it. So normally, so the dipole coupling contributes to the Hamiltonian. Do you guys remember did you guys go over what's the spin operator for the dipole interaction? What is this? ICSC, which is very similar to scalar coupling. So not surprisingly, the dipole interaction manifests itself in the exact same way that scalar coupling manifests in terms of the splittings of resonances. So here's an example of a CH bond. This is an HSTC. It's decoupled in which dimension? So normally you have so if I didn't apply any decoupling, what would I see? 4 peaks. So clearly this spectrum has been decoupled in which dimension? Fourth dimension. So the splitting is only in the carbon dimension. And the magnitude of that splitting is the one bond scalar coupling. And normally the one bond scalar coupling is interesting. Actually, by the way, one bond scalar couplings are interesting, but we're not going to cover that. But I think they're underutilized. They actually depend on interesting things like antibody and so forth. But nobody bothered to measure the one bond scalar coupling. Other than if you now partially align the sample and repeat the measurements of the splittings, you get a different number. That difference is the dipole number. Because now you're measuring J plus D when it's aligned, and it's only J when it's not aligned, so you subtract the two. The dipole contribution, let's go through this now. This is a very good, healthy exercise. I have an NH bond. It's parallel to the magnetic field. What will the sign of the dipole coupling be? So it's negative. So remember, if there's a negative, the product of the gammas, and you've got this. So you've got really 3 things to think about. You've got the minus front, you've got 2 gammas which matter, and then you've got the negative charge. So what's the gamma of magnitude of both? This total is positive, because the gamma of nitrogen is, so gamma of nitrogen, so you gotta be very careful, because the splittings can go this way or that way, right? So the gamma of nitrogen is negative, so these two multiply each other to give you a positive. If you're parallel to the field theta is 0, we get +1, plus, right? But if that was a pH fault, what would your dipole coupling be then? You have to think about that, right? So many common errors are like forgetting that swapping the sign, and then you're like, my dipole couplings make no sense because you forgot to take into consideration the gamma contribution. I like the NH bonds a little bit better because NH bonds are nice in the sense that when it's positive, it's parallel to the field, and when it's negative, it's negative. So it follows the P cos squared theta minus 1 over 2, because the minus cancels with the minus, and you get a nice thing. The CH bonds being a little bit annoying. Anyways, okay, that's one reason when we study proteins, because AIs are nice, you know? Okay, so that's how one measures in the case of magnetic alignment, in the case of using an ordering medium. And phage, as I said, is a very wonderful, generally applicable tool to align nucleic acids. And by the way, there's some beautiful stuff taken about the phage in the genome by Anna Grimston to understand the DNA and its properties in the phage. We're using PF1 phage. Unfortunately, as my lab will tell you, this used to be commercially available. PF1 phage you can buy it very readily, but now that company shut it down. And so we're in our lab, nobody can buy phage, and also nucleic acid in our people are very sad, but we're going to try to make it in our lab this summer. So if you have any phage, anyone out there, talk to us in August. Hopefully we'll be able to make it. But so again, here are the two mechanisms of alignment. We mentioned phage at the top, but we also have this magnetic alignment. And here I'm showing you the chi tensor, by the way, is called the susceptibility tensor, or chi tensor is denoted by a chi symbol. And so again, every little base normal has a little chi susceptibility tensor, which just means that if placed in a magnetic field, that chi can become a little mu, which is a magnetic moment, so it interacts with the field. And so as I mentioned before, when you add the chi tensor, because it's diamagnetic, it likes to be perpendicular to the field. So when you align an RNA in the magnetically, it will be perpendicular to the field. Whereas spherically, if we go back to my example, the most likely alignment for my pen sterically is to be parallel, right? Because this is so you get parallel alignment in the phage medium, perpendicular alignment in the magnetic field. Now, of course, this alignment assumes a rod-like shape. Your RNA could be complicated looking, and then its alignment could be more complicated. We'll come back to it. But as I mentioned, the way you measure this splitting is easy. For phage, you add the sample or remove it, you get a nice juicy 15 hertz. That's a sizable RDC in solution stage. But when it comes to magnetic alignment, you have to measure the splitting as a function of field, something that we can readily do here at MISDC, thanks to the availability of all the different fields. And you just measure your isotropic, your splittings, they're not isotropic. So for anyone who's ever measured a J coupling value on a nucleic acid at higher than 600 megahertz field strength, rest assured that J coupling has a dipole contribution of some sort. And what you can see here is you, again, plot the splitting as a function of B squared. You expect a linear dependence. And then you interpolate to 0 to get the scalar coupling. And then the difference between the 0 and the highest field is usually what we'll call our dipole, our RDC contribution. So you need to do the field dependence. What's the beauty of magnetic alignment? Why do we like it? Don't need anything else. You worry about the phage. Is the phage messing your sample? So it's nice to be fully free. There's an additional advantage which I'll describe in a second. Okay, so now the next question is, so I figured out a way to align this. And now the question is, which RDC am I going to measure? Right? Which RDC is the most valued? And so in general, in life, if somebody asks you, you have different things that you can measure. They all have the same angular dependence, right? Every bond vector has the P cos squared theta minus 1 over 2. So there's really no value to one. If you're looking at a base, any bond vector on the base tells me something about the angular orientation of the base. There's really no particular value for one bond vector versus another in terms of the theta distribution, right? They're all telling me something about the base. So all else being equal, I have an aromatic base shown here like guanine, and I have some choices. I can measure carbon-carbon RBCs, carbon-proton RBCs, carbon-nitrogen RBCs. No, I can do two bonds, but dipole coupling is a through space interaction. So actually, I don't even need to have scalar coupling to have a dipole coupling. I could actually measure dipole couplings between things that don't have scalar coupling with the appropriate experiments. And so, given all this can be stored or can be stored, and you've got all these different RBCs you could measure, what would be your criteria for what bond vector you would tell you? And by the way, this is true for any experiment. Like you measure stuff. What is a desirable? You want to be able to see the signal for sure. Why do you care about sensitivity? That's true. For what? Why does that matter?
Because we think you make the signal to be less intense, so to make us see the signal even steady.
Right. But more generally, what happens if something is, if I have a very sensitive experiment, I get a very sensitive measurement, what does that mean about my measurement? It will have a small error, right? No, very important, because I want to measure in the ideal world, to say to you, hey, this is a very nice dipole coupling, it's 20 hertz. Well, does that mean anything? No, because the question is, with what precision can I measure? If that 20 hertz comes at the error of plus or minus 30 hertz, that's a useless 20 hertz. So the quantity that one needs to optimize is the magnitude to precision ratio. If you can measure something with a precision of 0.01 hertz, then 1 hertz could be great, right? So it's a trade-off of those two values. And in fact, the reason we're going into solution is to measure things precisely. They're smaller than the solids, but we want to have an optimum trade-off. We don't want to then have we want to have the right signal to noise ratio, basically. Yeah. So therefore, who has the biggest dipole? So let's say who would have the biggest dipole? Directly bonded or two bonded things or p-bonded things? Directly bonded shorten the distance. Now comes the gamma, which but you can't have directly bonded protons. Also, proton dipole couplings are a pain to measure because if I'm a proton and you're a proton, I'm dipole coupled to you, and this multiplet structure gets complicated. So, in addition to the distance being more than 2.5 angstroms between any two protons, which diminishes the magnitude, is also so proton dipole coupling is kind of a rarity. So what's the next best thing? Proton carbon or proton nitrogen? Who would you like more? Let's ask the question. Who has the bigger dipole coupling? Proton carbon or proton nitrogen? So you would say proton carbon is great. It's better than proton nitrogen. What other thing do you care about based on what we discussed? So besides the magnitude, we still have to worry about precision, right? Who can I measure more accurately? A CH bond dipole coupling or an H bond dipole coupling? What would that depend on? I'm doing an experiment, and I'm measuring. I want to measure the splitting of the resonance. What determines the peak position is, like we discussed, sensitivity. So we have the alignment and the sensitivity. And who enjoys better alignments, nitrogen or carbon? For the same reason that it has a smaller dipole coupling. Right? So on the one hand, you say, no, NH dipole couplings are smaller. Well, the dipole interaction therefore contributes less to relaxation. So it's an interesting thing that when the relaxation goes into the square of the dipole interaction. So as a matter of fact, given an H bond, your favorable relaxation is greater than the magnitude of reduction. So actually, an H bond are more. That's why in proteins you guys have a fun time For those who do protein, amides are one, the nitrogen, also the CSA tensors of the carbon aromatics are higher than nitrogen, so the CSA relaxation contribution. So the question of which dipole coupling you want to measure is a complex, it's nuanced. It's not just fit enough to over the biggest, you have to think about the relaxation properties of the readout that they're achieving. But generally speaking, NH-CH bonds are the wonderful sizes, and then the minute you go to CN, what's the bond length, by the way, NH-CH bonds, what is the bond length for? Anyone know? One. You guys, every protein NMR person should know. In my opinion, what the NH bond length is in AIM. It's a big question. Because the NMR guys go crazy about containing vibrational frequencies, the quantum effect. What is it about? What is your favorite? And by the way, everybody has a different answer. I bet you have a different solid state answer. What's your answer for the NH bond length?
0.3.
Oh, 0.3. Mine is 1.04 for AIMs. I don't know where were you. They just know this thing. So what is it for CH bonds and roughly for a CH bond? Is it longer or shorter? It's a little longer. It's a 1.08. It's actually shorter. Why did it be shorter?
This carbon is older than that.
I don't know why it is. Theoretically, a little longer. But what is the carbon? How big is a carbon bond? Like on a C alpha beta or a CC?
Single.
Single bonds. Yeah. How long is that? Is it shorter than 1 angstrom or longer? 1.4 angstrom. So if I have, here's the problem set, we have problem set. I have a carbon, what is the ratio of a carbon dipole coupling relative to carbon proton? Based on the gamma, 4 times bigger. Based on the distance, cubic. What's 1.4 cubic? 1.
Actually, it is 1 versus 1.4. The 1.4 cubic.
Yeah, what is 1.4 cubic? 2.7. So you get a factor of 2.7 from the distance, not small. And you get a factor of 4 from the gamma. 4 times 3 is 12-fold small. And what are you getting in return? Well, the carbon is still suffering dipole relaxation because it has a proton. Now, if you pick carbons that are kind of not protonated, you might recover better relaxation because you don't have a proton. That's CH. So for a typical CH bond, what's the dominant mechanism of relaxation? I'm a carbon. I'm using the carbon to measure the splitting, which what we know we do. What is the dominant contribution to relaxation of the carbon? To the T2. You have the dipole part, you have the CSA. Who do you think dominates? At 600 megahertz, let's say. It's actually the dipole. The dipole, for NHs, unless you get to 800 to the gigahertz or 800, at a gigahertz, the CSA is field dependent, and amides, proteins, at a gigahertz, the CSA and the dipole equal each other. But when you're at lower fields, the dipole is dominating. The CSA is small. So generally speaking, rule of thumb. Now aromatics, carbons, their CSAs are larger. So actually, at 800, it's roughly 50-50 CSA and dipole. But the point I'm trying to make is that the CH dipolar interaction is a major contributor to relaxation. So you can try to get rid of it by having a carbon-carbon bond, so long as they're not directly bonded to protons, But then you have a problem trying to eliminate, etc. Anyways, the point that I'm trying to make is that carbon-carbon bonds are generally not interesting to measure because they're 10 times smaller, and it's not really clear you get any benefits from that versus the CH bond. Especially when you have an aromatic base that's rigid. We don't think aromatic bases are, although they do buckle a little bit, but we can approximate them to be basically rigid structures. So once I have 1 or 2 RNCs, I don't need more. So therefore, even though when you see this figure shows you the various magnitudes of the RNCs based on the gammas and the distances, we normally go for the juicy, big protonated carbons protein and nitrogen. I mean, anyone else who's measuring carbon RDCs, you should interrogate that paper very carefully, or the person, and say, are you sure you're getting any benefits from that? Now, there are very quantitative measurements for C alpha, C beta couplings, for example, where it could be worth doing. But there, it makes sense because there's a degree of freedom that you're trying to get to. But in a nucleobase, if you already have a CH bond, there's no value of getting another carbon-carbon. It's basically, it's going to contribute very little signal to the. You had a question, I interrupted you.
Isn't there like more variance in the distance between the nitrogen and hydrogen?
Is the distance vary? Does the NH distance vary? Yeah, absolutely. That's a great point. What does it vary with? At the what?
Like the factor seconds.
Oh, you're talking about the dynamics. Oh, totally. So the 1.04 number accounts for the 0 point energy by quantum vibrations. So you must take into consideration the fluctuation. So that's something that one has to consider when you consider what the NH bond length is. But I thought you meant more like
in terms of the
hydrogen bonding. So I am hydrogen bonded to you. I have a bonded H to me. What determines the NH bond length? You know? It's actually the pK. It's the difference in the pK. Your pK, and you want to relate the length of the NH bond and the hydrogen bond to the pKs, and that does vary. Now, actually, that's a good point because I don't think we take that into consideration for the NHs in particular. I don't know if people have actually, considered the fact that the bonding could be different for different hydrogen bonding states. I don't know. It's a good point. For the CH bonds, those are not hydrogen bonded, so there's not much of a consideration. But for the NH, whether it's outer plane or the length, that to be an important parameter. But we normally assume it to be, well, at least in solution, is 1.04 angstrom. And so you need to know the bond length to analyze RBC levels. That's not assumed to be a known. Now, imagine that I screw up and I say you are 1.04 NH, and in the CH bond I use a wrong bond, like a 1.2 angstroms. Those two sets of RDCs are not going to be able to be reconciled. But if I have the right bond lengths, but I scale them up and down by a constant, all of that can be absorbed in alignment tensors, which I'll discuss. So what I'm trying to say is very important to have the ratios right. The absolute scaling, you can live with it because it will just impact the absolute alignment tensor, which we'll go to in just a second. Okay, so then you can ask the same question: what are the right dipole couplings to measure the protein? And since this is the nucleic acid lecture, I'm going to skip that to it. So these are the magnitudes of the dipole couplings. Again, the AMI NH is a very desirable one, but so is the alpha H alpha with the much larger dipole. The alpha H alpha, also the resolution of NH is great. So the other question is how will resolve the spectra. Like obviously that's also important and it's part of precision. Okay, so there are many experiments to measure splittings of resonances. Unfortunately, we don't have time to go over the wide range of pulse. Did you say up until 3? Anyway. Yeah. So there are many different ways to measure splittings of resonances. And we don't have enough time to go over all of them. Maybe I'll say a couple of things. One is that each spin has its own properties, and different techniques will be more optimal. So there isn't like one. The reason, as is always the case with NMR, there are multiple different schemes, and which works best depends not only on the spin system but also the sample. If it's a big sample, small RNA, big RNA. So that's why you have this wide range of systems, whether it's a proton-proton coupling versus a proton-carbon coupling. So there's a wide range of experiments. The thing that I'll maybe point out is that in addition to measuring splittings, which is very obvious, now when you have a splitting, it's disadvantageous because you have double peaks, and in NMR, we always are aware of overlap. So you get to a fun experiment where you encode only one resonance, where in your spectrum, you only have the one resonance or the other, not both together. So then you can measure the subspectrum in one experiment, the subspectrum in the other experiment, without doubling the piece. So you guys did in phase and anti-phase. This is this. Okay. What you are tasked with developing an experiment that would only allow you to see one component of the level. And you're allowed to add and subtract. In the pulse sequence, you can run it in a way that, generates in phase or anti-phase magnetization with respect to scale. So normally, when I have a doublet like this, what do we call this doublet? What's the functional form of the splitting? How does it encode it? Trigonometry. This is, so I have chemical shift, which is, let's say, cosine omega t. But then I have the scalar coupling. How is that encoded for this? Cosine, cosine pi dt. Right? So cosine pi dt, cosine omega, in phase, double. Okay. So what else can you have besides in phase doubles? What's the other form? So what does that look like? What do your fingers? You need your fingers. Okay, so it's this, right? And that depends on. No, you said slightly. This is my opinion, right? Okay, so I can prepare my experiment in such I can design my experiment in such a way that in the indirect dimension there's an evolution period during which I either am evolving in phase or anti-phase. Okay, so if I have these two, what would you do to generate one component? Some, right? So sum those two, you get this. Subtract, you get this, and then artificially you get positive. So that's the basis of, for example, the SPE method, or in the ICAP experiment, in phase, anti-phase, allows you to run experiments and select at will one component or the other. And this is not perfect because the different spins have different scalar couplings, and so you have to tune it to a particular scalar coupling. So you'll get perfect cancellation for the one you tune it for, but it's in small variations, and you'll always be a residual. When you do the subtraction, you will always have a residual, but it still works. It's enough, it's suppressed enough that you can actually get better. So that's one trick. There are many other tricks along those lines to kind of reduce overload. But the idea is to measure the center of the peak. Does anyone know what is the other way of measuring a scalar coupling that has nothing to do with the position of the peak? You're not allowed to, no position, you're not going to measure the frequency. Yet somehow you can get the scalar or the splitting value. Does anyone know how to do that? How do you encode the scalar coupling in a line sheet? That's an interesting idea. But in the medium of the Mars, you can encode as you wish, right? So you have to encode the scalar coupling into some. Line sheet is interesting. What else could you encode? How else could you encode scalar coupling? Into what feature of the line? Besides its shape. The spinnacle? Yes, you're saying like evolved. So imagine so you just said we get, this is cosine pi gt. T is little t. Little t that I Fourier transform. Very important, right? Because since it's got a t, it's part of the fluctuation. So then when I Fourier transform, I'm going to get split. What would happen if my little t was some constant number that I control? So imagine I have cosine pi g delta multiplying my cosine omega t chemical shift. That tagging term, that cosine pi delta, will it cause a splitting? No, because it's not being Fourier transformed. It's got a delta. The only time you get a splitting is the interaction is evolving as a function of the little t. Let's call it little t1. or T2, So now let's imagine I do that, just for fun. I'm gonna be like, okay, I'm gonna set my little delta to give me a cosine that's 1. So I'm gonna set pi j delta to be 0. Right? If I set pi g delta to be 0, I get 1 for that number, agree? And so when I measure my signal, I get a nice peak, and I'm like, my wonderful peak. Great. Okay, now I vary delta. I mean, I don't make pi j 0, I have a finite number because I'm in control of the delta. Now the cosine is not 1. Cosine pi j delta is not 1, it's some number. So when I measure the new spectrum, the intensity has been diminished in a way dependent upon the scalar coupling value j. Because if j is bigger, we're quickly around the cosine. If it's small, it's not. So you can encode splittings in the intensity of the resonance. And then you measure the same resonance as a function of varying the little delta, and then you flip that to pi j, cosine pi j, cosine pi j that. So you can, by NMR, encode j couplings in the intensity, but then you have to do multiple measurements, varying that contribution so that you can actually solve for the j value. Those are very powerful quantitative approaches. And the nice thing is you can see that how well you get a spitting, because you could have done cosine function, right? And yeah.
Any other, it's like making delta speeds.
It's
like, it doesn't feel any different from this normal evolution for if you're taking things.
No, because I'm not, the j coupling is, it's not involving the function of little t. Right? You mean when you vary the delta?
Yeah.
Yeah, but I'm not, but because it's a constant time, and there's no evolution of the function of the spectrum, you never get split. Whereas if you're constantly varying it, let's say as a function of T1, is that what you need? Well, then you're going to get split. You see what I'm saying? So it's critical that you do not, otherwise you're going to end up with a little t. And the little t will end up manifesting itself as a split. So the name of the game is to evolve little t as a function of chemical shift. So what the term you want is you want a cosine omega, cosine pi j delta, and then cosine omega little t. So what happens is the chemical shift evolves, but the j coupling evolves for a finite period that you control, and then you vary it. Last time in class, I think we ended up veering here, and I started talking about pulse sequence development. Let's not do that. But any ideas about how that chemical shifts evolve, but not like how chemical shifts evolve freely, but that the scalar coupling evolved in a constant time.
You can build typos.
Exactly. So I can control the j coupling evolution by means of applying a 180 on the other groups and keep the chemical shifts all high. And you can do it in such a way that the total evolution of the j coupling is a constant time. It doesn't change the function of the little t level. Right? And so maybe we can, for the next, maybe tomorrow, I can give you a little example. Okay. So this is just an example of the IPOC experiment. So first now, when you are, now comes the trade-off that I mentioned earlier about you want to be greedy. By the way, NMR spectroscopists are greedy. We're greedy because our signal is never sufficient, right? So we have to squeeze the last bit of juice from every little experiment. And so in this particular case, you have the phenomena of Trozy. Oh, great. Okay, so Trozy also is an important consideration when you're making a splitting of a multiplet, because in the case of, for example, a NH1 vector, you have the management component of the doublet that enjoys the mutual cancellation of the dipole and the CSA relaxation mechanisms. And the way to think about that is, remember my little magnet? Remember I said, oh, the proton is experiencing a field. And then if it goes perpendicular, it's experiencing another field. Well, imagine now the CSA is always opposing what the dipole is doing, so that whenever the dipole says go up, the CSA says go down. And whenever the CSA dipole goes up, so then you get mutual cancellation of those two interactions. that particular nucleus will enjoy much better resolution when you look at the Trojan element component of the doublet. And so here we're seeing the Trojan component of the nitrogen. So this is the nitrogen chemical shift, and you can see that here I have a very nice juicy signal, the Trojan component of the doublet, whereas this component here is the one that's getting the double whammy of download of the CSA. So whereas in the proton, from the proton's perspective, I don't have this phenomenon. Why not? Why is there only a Trojan thing applied on the nitrogen side of the system, but not the proton? Why isn't the proton also having a Trojan effect? So remember, it relies on the mutual character. Okay, pretty good.
I was thinking of like we talked about this in the lecture. I was thinking about those three terms in the relaxation where you have like a cross-correlated term. There was a auto relaxation of the dipole atom.
Yeah.
So for the hydrogen energy.
No, you're totally right. So there's a cross-correlated relaxation term, which is across the 2AB term. Like you have A plus B squared. So the A plus B squared gives you A squared plus B squared plus 2AB. And that's the cross-correlated term. That's one way to look at it. A very simple, maybe even simpler way is just the physical picture that I mentioned, where you have like the field of the CSA opposing or not opposing. But in order for cancellation to occur, you must have what? Besides the dipole interaction, you have to have CSA, right? So, as I said, the CSA is field dependent and it depends on the nucleus. And for a protein system, the CSA magnitude becomes equal to the dipole around 1.2 gigahertz or 1.1 gigahertz, you know? So, but what about protons? Do they have a CSA? Very small CSA. And I saw very small CSA density. So, from the proton's perspective, there is no benefit to there's no difference between the Trojan and anti-Trojan component. So therefore, you select from the nitrogen's perspective the Trojan benefits, and then you split it in the proton direction. There is a small effect, you can do the tiny, because protons do have a finite CSA, but it's much smaller. So you leverage the Trojan phenomenon effect in the nitrogen dimension, and then you read out splitting. You don't want to read this on the top because that's very weak in sensitivity, right? And by the way, the scalar coupling is always the same, of course. From the nitrogen, you know, J coupling split in the nitrogen or the proton are always the same, right? There's no difference. So these are the considerations that you would have to when you measure splitting. Now, we always think so. Every resonance has its own uncertainty. You know, one thing we know from NMR is that the same type of spin has very different broadening depending on who it is, because you can have line broadening composition, some exchange broadening, right? So you really have to worry about the error in measurement on a per resonance level, you know, and not ascribe a uniform error. And the best thing to do normally is to measure the RDCs or the splitting using two different experiments. Since you have a large swath of experiments that you can do to measure the same splitting, what I think is always important and good to do is to measure the same splitting two different ways. So what you see on the y-axis is measuring it as a splitting along the carbon dimension versus the proton dimension. Just the two simple things, right? Now, by the way, the proton dimension also suffers from proton-proton couplings, so that H5 and H6 is the scalar couplings, you get splittings. But generally speaking, it's always advisable to measure something two different ways and estimating your uncertainty based on the root mean square deviation or whatever physical way you want to do. And here you can see the quality of those measurements done by a very, very smart postdoc. These are, I was a postdoc in Europe, but this is an example of that. Okay. So now, as I mentioned, you should still be always paranoid if you're going to measure these RDCs about what if my RNA loves phage and it's binding. So what would you do, obviously, to check the solution NMR that something is protecting your sample? What's the obvious thing you do? Check the chemical shift, right? And you say, oh, if my chemical shifts are changing, then maybe there's an interaction happening, or maybe my buffer is off. Except that you should be aware that you are expecting certain changes to occur due to alignment. Why? Because the chemical shift anisotropy also is no longer averaged to zero. So if RBCs are averaged to zero, they contribute to splittings. If the chemical shift anisotropy is not averaged to zero, they cause a shift in the net shiftage. And if your CSA is very large, that shift can be substantial. Now you might say, oh, that's great, why don't we measure our CSAs? Yes, you can measure them. They're smaller than RDCs, but they also depend on the CSA test. So the beauty of dipole couplings is, they're like bread and butter. Like a dipole coupling, all you need to analyze in one bond dipole coupling is the volume. And then you go home and you do all the structural analysis with that. But if you're going to measure RCSA, what do you need to know to interpret that RCSA? You need to know the second rank CSA tensor, which is a wonderful, rich source of information in and of itself. But unfortunately, that very, in a way, and hopefully we will be collaborating, whether with Angela, to look at many of those CSA tensors independently. Because that would they value themselves. Like the bond has some information. You could argue that an H bond has information about hydrogen bonds and so forth. But the CSA tensor is really very rich information. But unfortunately, if you don't know what the CSA tensor is, every cell. It's like taking a variable bond length and it varies in ways that I don't know what dictates that variance. Are you going to analyze those RDCs? No, because I have no clue. I can't decouple the orientation from the bond length. In a similar way, our CSAs have that complexity, but on the other hand, it's also a lot of rich information. But nevertheless, magnitude of parts per billion can be expected in a nucleic acid and line in phage. In the carbon dimension, nitrogen CSA is too small. But for the carbons, you can see some shifts, and so you shouldn't freak out completely. That now, when you see such shifts for the sugars, carbons, notice here I'm only showing. Oh, I didn't say okay, and sugar. Oh, sorry. For the base, it's 170 parts per billion. Notice for the carbons, it's much smaller because the carbons have much smaller CSA. Sugar carbons, smaller CSA. You need a lot of aromatic electrons to juice up the CSA. So sugar tends to have smaller CSA than the first which if you sugar, there's interesting all of it. Okay. So now you might think, I'm going to go back if you don't mind. Sorry. Yeah. So imagine I measure my dipole coupling, and it's 20 hertz for one of my bonds. So I measure the 20 hertz here. What can I solve for? What quantity? So I measured the dipole coupling. Finally, I got my measurement, got 20 hertz. And I want to learn something about my molecule or something about my bond character. Okay, so I measured this quantity called D. All of these guys are, what can I solve? What have I actually measured?
So actually, those arbitrary measures and even you can fix it.
That's it. We know that. So I can solve for. I can solve for theta. Interesting. Let's go with it. So let's say I have 20 hertz. What a great exercise. I measured 20 hertz. And I make it equal to this term. Anyone know what theta should be roughly? What theta? Let's solve for theta. So I can tell you this term is roughly, for, let's take an NH bar. This term is like 24,000 hertz. This term. Notice it's units hertz because the angular term is unitless. So I have 24,000 hertz here. This measurement is 24. Let's make my dipole coupling 24 hertz. I measure the 24 hertz dipole coupling is equal to 24,000 times that angular term. So theta will be, now we have to solve for theta. You guys can do it. But I will do it because I'm a PI, I can do it right now. It will be, what do you guys think it's going to be? Because let's say, remember, if theta, if the argument in front of this 24,000 and theta is 0, it would be 24,000. but I'm measuring 24. If it was 90 degrees, it would be 12,000. But I'm measuring 24. So my 24 maps where on the function? Near the magic angle. So you're Jim, I feel very bad for you because you're like, I've got 20 hertz. So your range is 20 hertz, 10 hertz, 0 hertz, minus 10 hertz, minus 20 hertz. And you're coming back to me saying, shoot, one of them is 54.5, the other guy's 56.2. They're all on the magic angle. What am I going to do with this? Does it make any sense? Isn't that straight? What's the problem? But it's good you did that. You're absolutely right. That's what you do. What sin did young Jim commit? You forgot about the average. Now, if this was average theta, if this function was phi cos squared average theta, that's a different story. So what you do when you measure RDCs is you determine the average of a function. Back to why I said that's why it was important to have the average of a function. So now, in order to unpack an average of a function, we said before, you need a distribution function, right? Except the distribution function is no longer sine theta. What is my distribution function? Oh my God, it's this crazy function describing the weird alignments, right? And I don't even know how to write it. Like there's no equation. And so how are we going to make progress? How are we going to try to unpack? And actually, is there a value to measure this average angular term, right? So it's an interesting question. Now, why is it that my dipole coupling is 20 in this picture? Why is my dipole coupling 24 hertz, not 24,000? What was the dipole coupling for these guys? What is it for these guys? What is it for these guys? So you've got a lot of zeros, right? So there's a lot of zeros that scale you down to 24 hertz, which contain no information, right? So there's a magnitude of alignment, which you are not taking into consideration. And by not taking into consideration anything with the bond vectors along the magic angle, you're basically putting the bond vectors along the magic angle to physically describe the fact that I have a bunch of bonds that are not aligned. Well, that's a stupid thing to do. Not very interesting, that's not a healthy thing to do. Because, of course, I know a lot of them are not aligned. So one needs a way to unpack the distribution pattern. And I think one of the most amazing results or facts is that you would think that a distribution function can be completely arbitrary and like would require so much description, right? Like imagine thinking about my molecule, it's got some, how many different distributions can you have? A gazillion, right? So I'm not going to have to like figure out how am I going to specify the distribution function? It turns out that the distribution function, the aspects of the distribution function that I care about, can be reduced into 5 numbers. So the distribution of the alignment of my molecule, despite the fact that it's complicated, can be reduced into 5 parameters, which define alignment tensor. So what are we talking about? So let me show you what we're going to do now. So here. So this is the angular term. And the problem with this term is that it's averaged over the function. And I want you to show here on the right, you should be very happy.
Why is 3 instead of 3?
Oh, sorry, guys. Good eye. This is the hopefully there's no other errors here. So now what we're going to do is we are going to have here's the magnetic field. And on this here, what we're showing is the molecular frame of my molecule. So you are now sitting on your molecule. This XYZ coordinate shows my molecule, its molecular frame. And relative to this molecular frame, the magnetic field is moving around, right? I'm sitting on my molecule and I see the magnetic field going in many different directions defined by angles theta. Okay. It turns out that Now, in this molecular frame, my bond vector makes these theta angles. Now, those theta angles I find very compelling. Why? Because they define the orientation of my bond in my molecule, in the molecular frame, not relative to the external frame, but external magnetic field. So what I want to do is have on the right here a molecular frame that describes the averaging of the magnetic field relative to the molecular frame. So that describes the alignment of the molecule. And once I have that, I can, for a given bond vector in my molecular frame, explain how it will be averaged. And the way you do it is shown here. So Sij are elements of an alignment tensor, of which there are 5, uniquely independent. Sij is a matrix, but it's traceless and symmetric. So traceless and symmetric means there's 5 parameters, which is the diagonal from 0. So you've got 5 elements. So there are 5 elements. Let's imagine we don't know who they are. But those 5 elements are given by this. This is now the averaging, but it's the averaging of my molecular frame relative to the magnetic field. So I'm asking the question, what is the averaging, for example, if I and j are zz, I get p cos squared alpha z minus 1 minus a half. This becomes 1. So if I know the average of t cos squared theta minus 1 over 2, imagine I have my PDP, and have in my PDP I have x, y, and z, right? Imagine I know the average of t cos squared theta minus 1 over 2 for x, unit vector x, unit vector y, unit vector z. Let's say I know those numbers. And I know the orientation of the frame that needs another parameter to define the location. Once I know the averaging of phi orthogonal coordinates, I can determine the averaging of any arbitrary vector by a superposition approach, where I take the vector, superimpose it on z, multiply that superposition by the z alignment, and this is what the expression means, right? So for example, take cos theta z, cos theta z, that's the cosine theta z projection, and multiplied by the order parameter SCC, or the alignment tensor SCC. So I have molecular frame, I know each of them averages. Now that I know that, I can embed any vector in my, if you tell me, once I know those elements of S, so if I know the F matrix, you can give me any arbitrary vector in my molecular frame, and I can predict what its t cos squared theta minus 1 over 2 will look like. And the very interesting and fascinating thing about this is that I only need 5 parameters before, no matter how complicated the distribution of the alignment, you can come up with the most complicated, you can imagine insane distributions of your molecule. In the end, they all average out in such a way that only 5 independent parameters need to be known in order to account for my dipole couplings in my rigid molecule. By the way, we're assuming here my molecule is rigid, where I have a molecular frame, I have vectors in the molecular frame, and all that's happening is a preferential alignment. And so therefore I need S. I need 5 numbers, 5 S numbers. If I know what those are, now if you tell me I have measured a dipole coupling, what can I solve? So now if I now have this equation, let's say I know the S alignment tensor, there's 5 numbers. For one per molecule, there's 5 numbers. Let's not worry about how we get those 5 numbers, it's important. But suppose you knew those 5 numbers. Now what can you solve? Yeah, he needs it. Yeah, you're right.
Orientation relative.
Which angles in this framework? Thetas. Now I can solve for the theta angle between my bond vector and the molecular frame, which is the structure, in a way, right? It's the orientation of the bond in the molecular frame. And that's money in the bank, right? As opposed to the magnetic field. So S, when you solve your problem, that you're ignoring the fact that the molecule is aligning. So the magnitude of S, by the way, S, if you're a solid state, SZZ would be 1, because you're fully aligned. But generally speaking, the element of the alignment tensor has values of 10 to the minus 3. So then you've defined an alignment tensor that already has absorbed the fact that most of the molecules are not aligned. And it allows you to then extract out on angular dependence only insofar as the molecular curve. Does that make sense? Very important. So, by the way, another important thing here is when you measure in NMR an average of something, the average of theta cos squared theta minus 1/2 is not the same thing as the average of theta. And it's very important to understand that. And then we have to worry about dealing with the averages, right? And getting rid of, in a way, we're getting rid of them. Now, there's a whole spherical Wigner rotation treatment of this. If anybody's interested, maybe another time in the pub, we can derive the alignment tensor. But it literally is like the Wigner rotation elements. If you have an alignment tensor of D2 0, it's the Wigner rotation elements of D2 0L. And those are 5 elements that you average out. It's like a 2-line derivation if you use spherical coordinates for why it is only a 5. But it's still a very cool result. And no matter how complicated the distribution of a function is in the model, the things that you can sense, or the parts, the second rank tensors only care about 5 parameters in that distribution function. So even though I can't describe, I don't need the full distribution to account for isotropy direction. And that's interesting. That's a simplified fact. Okay, so therefore, my dipolar coupling, so for every dipolar coupling, I have a different vector, different alpha, right? So in my molecular frame, I have many CH bonds, they all have slightly different alphas. So here's the matrix equation. So every dipolar coupling has a different set of, now I've changed it to theta, sorry. Think of these as theta as alphas. Those theta are alphas, but they're the molecular frame alphas, multiplied by the alignment tensor. And so these are the molecular frame thetas. So there's always one set of 5 alignment tensor parameters applicable to all my vectors. Therefore, if I know the alignment tensor and I know my structure, meaning the orientation of bond vectors, I can predict any RBC. Conversely, but in general, when you start, you don't have the alignment tensor. I mean, you measure this, maybe you have a model for your structure, so you have some of this. So you really have to get the alignment tensor. So either you know this and generate that, or you know that and you generate this, right? That's the trade. Now, what happens if your molecule is dynamic? What do we have to do to those equations?
You have different.
Oh, I like the different S. Let's keep the S the same, because let's imagine my global shape stays like this. So my S is the same. But my bond vectors are moving up and down. So it's not one static vector. My vector is average. Where will that show up? In this statement. In the alpha now has to be average, right? Because you can calculate for this structure where the bond vector was here, it would have 1 theta. When it was here, it has a slightly different theta. And then you average them, and now you have an average over the cosine. But that would be important to consider. And that is why RDCs can also be sensitive to internal motion. The global alignment motions, which we generally don't care about, the alignment tensor, is captured by S. So anything related to the overall alignment and all that busy stuff, S is absorbing. But within the molecular frame, you could have internal motions, which will further average the dipolar couplings. And so you have nested averages. You have the global average, and you have the internal average. And this is the way of separating each. Okay. So now here's the alignment tensor, which I want to explain a little further. Just like any tensor, how would we define a CSA tensor in the molecular frame? How would we go about defining a CSA tensor? What I need, if I wanted to, I have a CSA tensor, what do I need to define it? Or specify? What? Yeah, but I want to specify my CSA. How do I do it? In your mind, what does the CSA tensor look like? Right, but in your mind, how do you visualize the CSA tensor?
So
You have an ellipsoid? That's interesting. What about like a little just orthogonal little orthogonal vectors with very amplitudes? centered on your, say, carbonyl. Right? And let's say you have a carbonyl. I actually don't know. Is the sigma ZZ along the carbonyl bond? It's perfectly sorry. Okay. So imagine I have a carbonyl. So first I have to specify in the x, y, z coordinates the carbonyl. Then I must specify the orientation of a thing that has three unit vectors that are orthogonal, each of which is a different magnitude, in some cases sign, relative to the carbonyl. So how many parameters do I need to specify this three-dimensional, the C-unit vector thing relative to a molecular parameters? How many angles do I need? What are they? But like how? Yeah. So what we can do is let's take the principal component. Let's call it sigma ZZ. To orient one vector by itself, how many angles do I need? So I have a vector in space. How many angles I need to define its orientation? One. So, but I have this, and I can do this, right? Like in polar coordinates, you've got two. Right? Because my one vector could be theta squared here, or it could be here. In my molecular frame, my molecular frame is not symmetric. I have a carbonyl, right? So it matters whether it's here or here. So two angles define the orientation of the principal axis. What else do I need for? And then I have to rotate around the principal axis to define where is x and y. Because those can also vary, right? So I need three Euler angles, or three angles, to define where the hell is this thing oriented relative to my molecule. And then I need two parameters because the sum of the lengths goes to zero. So this is an anisotropic tensor, and its properties are that the length of the vectors sum to zero. Therefore, if I have two of them, I have the third. So I need two amplitude numbers, three Euler angles, 5 parameters total. The same tensor applies to the alignment tensor. 5 parameters. Except unlike CSA, which I define to account for our CSAs and relaxation, my alignment tensor is a second rank tensor that defines the alignment of the molecule. They're both serving the purpose of describing how those zero functions average. And it's very interesting that they use the same kind of underlying mathematical structure. But that's so therefore, when I solve for the tensor, when I solve the alignment tensor, the principal axis defines what? In the CSA, it defines the principal direction of the CSA. If I measure the principal LDZ of the alignment, it's the average orientation of the magnetic field relative to my molecule. So I have a molecule, and I solve where is SDZ, where is SXX, where is SY. SDZ is the average orientation of the magnetic field. X and Y is the propensity for you to then fluctuate the field along the X. Y is the one where you fluctuate the least in the distribution. If you're axially symmetric, X and Y are similar. So if you're a rod, the magnetic field will be on average parallel to the structure, and axially symmetric because there's no preference for X, Y, but if this was a rectangle like this would be C, but there's a difference between X and Y. Because I will reach the alignment, there will be a difference between this alignment order and that alignment order. So therefore, the alignment tensor, so therefore, if there's two molecules in two fragments in a molecule, and I ask one of the fragments, hey, where is the magnetic field? I think the magnetic field, let's do that exercise. So I think NCZ is in this direction. If I ask this blue domain, where is the magnetic field? Oh, on average, I think it's over there. Okay. Hey, you, where is the magnetic field? Oh, I think on average it's over there. Now, the way I'm solving for the alignment tensor here is I'm assuming I know the structure for the RNA because there's like helices, unlike protein polyadenine proteins, you can't model them as idealized helices. Many RNA helices can be actually modeled as a good approximation, like idealized A form. So I take the red helix RDCs, the known structure, and I solve for the alignment. Right? So I know this, I know that. Solve it for the red. Then separately, take the RDCs for the blue, solve for the blue alignment tensor. And I solve it, and I don't know their relative orientation of the two helices. That's the thing I'm interested in. So what I do is I say, hey, red, where's the field on average? Oh, it's there. You, this way. Okay, to solve the structure, rotate the helices so that they see the same average direction of the field. That's like if I told you where the north direction is relative to Italy and where it is relative to the States, and I have the two countries, separate, you can determine the relative orientation of the two by moving them in such a way that they see the same north direction, right? Exactly the same way, one can build structures of RNA, and by the RNA helices, RNA is, one could argue, are nothing but collections of RNA helices. I'm simplifying, linked together in space. And we would love to know the relative orientation. And the power of the RNCs here is that I can tell you the orientation of those two helices regardless of their distance of separation. Isn't that cool? Like my two helices could be, as long as they're connected by a rigid framework, light ways away from each other. I can tell you the relative orientation because at the end of the day, they must see the same magnetic field direction, right? So therefore, this turns out to be very important because in the gases, we have a very low density of protons, and we have very few long-range NMRs. The wonderful NMRs that bring globular proteins and constrain their structure. Nucleic acids are extended structures with very little protons, and the error that compounds from distance measurements locally creates great uncertainty in the global chain. Whereas RDCs are literally global measurements. They don't care about this. And I can measure them in great abundance, and so therefore it is very constrained. Now, so the length of SDZ here in this picture, what is the length of SDZ measurable? How long? The maximum line is 1. That's all. We are generally like 10 to the minus 3, 10 to the minus 4. Okay, so if I have a rigid structure, and my two domains are rigidly connected, and I ask one of them, the red helix, how aligned are you? 10 to the minus 3. Blue helix, how aligned are you? What should the answer be? They're part of the same structure. Can one of them be more aligned than the other? It should be 10 to the minus 3. Right? So you say, okay, you're both 10 to the minus 3. But now I do an experiment and I measure it, and I end up with like the red helix is 10 to the minus 3, and the blue helix is left off. It's 10 to the minus 4. The amount of alignment, the red guy experiences more alignment than the blue. And let's say the student did not make any mistakes, no problems with the RC measurements, the helix coordinates assumption is perfectly correct. How could that be? What would that be? How would you rationalize? Do they have the same alignment tension? Do they have the same alignment? No. One of them, yeah. So, yeah. If there's motion, you can reduce the alignment, the apparent alignment. And let's pick a fun example. Imagine I'm a bond vector in a protein, and my bond vector is moving isotropically in space relative to the protein. The protein is nice and folded, but I have a bond vector that inside, relative to the molecular frame of the protein, is sampling every single possible orientation completely isotropic. Now I align the protein, and then for every alignment, the vector samples the whole space. Next alignment, all the space. What would that probably be for that vector? Be 0. If you ask them, what is your alignment? What would the vector say? Yeah. So if you ask anything, if you ask that bond vector, what is your alignment? What would it say? It would say 0. But if you ask the rest of the vectors, what they would say is unaligned. So in this particular example, I said very intentionally, the blue one had a smaller alignment tensor, as shown here. So the blue one had the smaller alignment tensor, the blue helix. But why is the blue helix less aligned? When I have two domains moving, I could say the red is moving relative to the blue. So why isn't it that the red helix is less aligned? Why is the one red dominant? Because it's more anisotropic. So when and a nice can I draw? So when I imagine this is super small, when it moves, it doesn't change the global shape of the molecule, but its molecular frames are going a lot of average. That's the perspective from the big helix, right? The small thing is moving around. It's not changing the overall alignment tensor, and it's just moving in the molecular frame. But if you're sitting on the blue helix, it's seeing a violent fluctuation of the shape. Isn't that weird? If you're sitting on the blue helix, from your point of view, the red thing is the big long red thing is moving like insanely. The global shape is changing all the time, and you're getting averaged enormously by the motion. But if you're sitting on the red helix, from your vantage point of view, the movement of the blue helix has no effect. And so therefore, yes, the red helix is more aligned than the blue. Now, what if they have the same leg? So let's imagine that both move. There is motion of two equally long helices. And I asked each helix, what's your alignment magnitude? What would they respond? The same. And what would you conclude? Is there motion or is there motion? How would you know there's motion? Because that's the result you're expecting if there were no motion. You couldn't tell. Okay, so suppose I have two helices. They're the same size. They tell me they're the same amplitude of alignment. Because you're in this class, you know better not to interpret that as no motion. What would you do to test whether there is motion? Lengthen the one helix, right? So elongate one, break the symmetry if you can. And as it turns out, RNA can engineer this easily. There are ways to maybe do it in proteins too, to like make the domain bigger or more anisotropy. There's some very interesting symmetry properties. If I have a oligomer, a trimer with CFE symmetry, this is a great question. So you have an oligomer with CFE symmetry, and I try to align in an ordering medium. Where should the SDZ direction of alignment be? Now you might say, oh, it has to be the symmetry axis, right? Because it feels good. Makes sense. And one way to think about it is if you pick any other angle, let's say this orientation, we'd run into trouble because there's another equivalent direction here, another equivalent direction there, and there must be a uniquely specified alignment tensor, and those two would average out anyways. And so to see these symmetry, so there's some, so when it comes to oligomers, the alignment is predetermined by the symmetry of the oligomer. That can be quite simplified. If you have C2 symmetry, these are the different kinds of. There are other constraints from C2 symmetry, like I showed an example of C2 symmetry. But depending on the symmetry of the oligomer, you can also pre-constrain the alignment tensor, which can, in some sense, simplify the analysis. Okay, so the more common equation that's used in, and I'll end here because you said pre, right? I should stop. Maybe I should stop for questions since it's 3:03 and pick this up next. So maybe I'll take any questions about the RBCs. Oh, by the way, so we described the averaging of the RBCs in terms of internal motions. And so what are the time scales that lead to the averaging of RBCs? How would you figure that out? So for example, in solids, when I'm trying to rotate the dipole couplings out to get an average Hamiltonian, how fast do I need to speed? Do I have to spin? Spinning downwards. What's that number? Right, the magnitude of the interaction, and how much it varies from one angle to the next. Right, like the delta between different. When I rotate the sample, I'm sweeping different magnitudes of the interactions, and I need to spin faster than the difference of these interactions to average them out. You know? In the same way, for the dipole coupling, let's say I have a bond vector in this direction and it has a value of 20 hertz. And then on occasion it goes like this and it has a magnitude of minus 10 hertz. Now, what should the time scale of motion be such that I would end up measuring the average dipole coupling? how fast, what do I need to get the averaging limits of the RBCs? Correlation, no, correlation time is not necessarily. So I have my one vector. So imagine I have one vector up here, and I get 20 hertz. Here I get minus 10 hertz. I do my splitting measurements. Let's imagine the exchange is super slow for fun, and they have the same chemical shares. But in one case, the value is 10 hertz, in the other case, the value is minus 10 versus 20. What would appear if I split it? What would I see? Would I see 10 hertz or 20 hertz? Or the average, if it's in super slow exchange? Huh? Well, so the data couple is either 20 hertz or minus 20 hertz or minus 7. And it's super slow. Like, let's say these two molecules, they're all tumbling, they're exchanging them. It takes 1 billion years to exchange. What will I see? You'll see both. You'll see this tumbling, you'll see that. Okay, so now I start to undergo motion. I want to, and then at the limit of super averaging, and let's say it's 50-50, I will observe plus 10 hertz, which is the average. But what's the time scale? That how do I think about what should the rate of the motion be to achieve that averaging? Faster than the difference. So what's the difference? 30 hertz. So how fast should it be? What time scale? Millisecond. So faster than millisecond time scale. And it depends on the magnitude of the RBCs. Right? If I have small RBCs, then I need to I can be slower, I still average out. And so if you are on the averaging limit, the power of RBCs for RNA, which are very flexible molecules, is that it will be the internal motional averaging will be captured by the RBCs for time scales spanning milliseconds, microseconds, nanoseconds. Now the weakness is you can't tell the time scale. You can't determine the time scale of the average. But the measurement will be averaged over all the configurations over sub-millisecond time scale. So that makes it very sensitive. Yeah? Okay, we'll continue tomorrow with more nucleic acid NMR and some applications of RT and then more assignments of science. How we assign.
Thank you.
Thank you. I have to write the recitation now, so I better go. Oh, it's you. Can I sit here? Oh,
Yeah, good. Nice. Are you ready? Are you ready? Can I ask you a question about this? No. You may ask. You may know about me. Among this, you show me like there should be a relaxation. So it should be originally filed, but then you can use something else. Like, like it feels like, yeah, it's great. It's like the core, you know, like feel much faster. There's also a lot of flexibility. You can store and talk about past. So you should be your store of the option here. It's a totally can't buy any stuff. Yeah. Oh, like the penny the square. Yeah, no. Doesn't stop you. It's like so many customers. Like so. How do you feel that? Tell me where this market is. I mean, now is the only question I see. I wonder if we whenever we didn't update the number up. I don't know. Oh no, I said everyone switching so we didn't. No.
Okay. This is going to be a really short uh, problem session of the sort where we're going to start discussing a problem that we had assigned a couple of weeks ago on dipole coupling, solid state NMR, and calculation of average Hamiltonians for some of these. We did an example in class where we talked about how to handle a time dependent Hamiltonian, which is average to zero on the magic angle spinning. And then we showed how radio frequency intervention with MAS and recouple dipole coupling in a way to affect magnetization transfer. So the example in class was Hartmann-Hahn phosphorylation. Then we had assigned a homonuclear equivalent that we will not be able to go over that probably in its entirety this time, so we'll come back to it in a later part of the session. I would say that this was a truly challenging problem to be assigned, particularly because it is a homonuclear Hamiltonian. It behaves in slightly more complicated ways, but I'll just go over briefly the logic of the average Hamiltonian, where we said that you have a dipolar Hamiltonian, which has some of these time-dependent components. And you have a second rank tensor, which gives you this component at omega r and a component at 2 omega r. That's necessarily always the case with any second rank tensor. And you have this is the space part and the spin part, which for a heteronuclear case is what? Spin part of the dipolar Hamiltonian is the nuclear I and S. 2YZSZ. For the example in consideration today is the homonuclear case, and does anybody remember what that dipolar Hamiltonian looks like? When you truncate it for the part that commutes with the Zeeman Hamiltonian. Yeah, something like that. I1 to Z minus I1 by 2. We'll simplify this in a minute, but what is the average of this over the rotor period? 0. So that's like if I just write HC average without any RF interaction in question, I just average this over 0 to power, and I get 0. Now the hope is that by introducing RF pulses, we can move into a rotating frame, sometimes called the interaction frame, sometimes called the toggling frame in the lingo of the NMR. We can move into a frame where this average of this interaction frame Hamiltonian, indicated by this tilde, is non-zero, right? And if it is non-zero, then transverse magnetization, or in this case actually longitudinal magnetization, will evolve under the dipolar coupling, and that will enable distance measurements, magnetization transfer, and so on. Okay. The first program that you were given in class was radio frequency, was called RFTR, and unfortunately, a lot of these sequences have different names. That pulse sequence looks something like this. It's, although you can just truncate it here if you like. This whole distance covers 2 rotor periods. and you place the pulses at exactly half rotor period. Okay, this is how this pulse program is constructed. So you have a rotor period, smack in the middle is a 180-degree pulse, and another rotor period, again a 180-degree pulse in the middle, and so on. You have one pi pulse for each rotor period, and this process is done any number of times, and that will end up in the evolution of the magnetization under the average Hamiltonian. The problem posed to you is under one rotor period or under say two rotor periods, the cycle of this average Hamiltonian, what is that average? And we got a few different answers from the class as a whole. So we're going to talk about those several different approaches. So, but before we do that, we'll talk about how you handle the RF interaction with the dipolar Hamiltonian. So if I were to write HRF of T, for the case that we discussed in class, we had something like this. We had a simultaneous spin lock on both I and S in order to engineer a heteronuclear transfer, and then we went into the doubly rotating frame, doubly rotating interaction frame, where we calculated the propagator corresponding to this, and then moved into this RF defined frame where the dipole average Hamiltonian was non-zero. And this was like for all time that you hold the spin lock, that RF Hamiltonian is just that omega ix plus omega sx, assuming you have x phase pulses in both. What does it look like for this pulse program? Between t equals 0 and t equals tau r, what does the RF Hamiltonian look like?
T equals 0, T equals R over 2 equals 0.
Right.
Or 1. And then,
In this case, 0. Yeah.
yeah, and then in the next half, it's like just e to the negative I.
This is the answer we got. Under a very critical assumption, which is
Pulses delta.
the length of the pulse, the duration of the pulse itself is extremely small. So small that I can treat the pulse as infinitesimal, right? As like taking almost no time. But does this make sense? Because before you have this 180-degree pulse, all your Hamiltonians are just by themselves. You haven't done anything. Does this make sense? Before the 180-degree pulse hits. That makes the RF Hamiltonian 0. But when the 180-degree pulse has to hit, you've rotated all your Hamiltonians by 180 around x, with the 180x pulse. Which is why I've created this rotation operation, e to the minus I pi, ix, which is a rotation around x by 180 degrees. Does this make sense? Every Hamiltonian that has a term that can be rotated around x will suffer a 180 rotation for that time period between the middle of the rotor period and the end of the rotor. Does this part make sense? So this is how you construct a piecewise RF Hamiltonian for pulse programs that involve these rotor synchronized 180 pulses, which is a different approach, but in many ways equivalent to having a constant spin lock. So spin lock is one way to do it, and that's for again variable duration. The other way to do it is use 180-degree pulses, and that's how we define for this block. I have an RF Hamiltonian is this before the 180. Then after the 180 it's back. Similarly for the third block, again the same. Then when we reach the fourth block, what is the RF Hamiltonian? it goes back to 0 because I've done a 180 minus x rotation. So if you were to define for that block, it would be e to the I pi x, e to the minus I pi x. Again, I guess you can define this as, would it be defined as 1 or 0? Maybe I have to look at my notes about this. Huh. I'll have to look back at that, but as far as yeah, this should still be 0 for some reason. You have something to say?
Maybe. Because if you integrate zero, just gonna, like when you're solving for that Hamilton,
Uh-huh.
and you integrate that, like, yeah. I feel like it's wrong.
Well, ultimately, what matters is the propagator. Right? Then your interaction frame is something like this. H here is HRF. So if you don't have a 0 here, this will become, you had 1, it looks like minus IP, which is, doesn't make sense. Anyway, I'll look back at that and I'll confirm why it goes back to 0. But does it at least make sense logically? Before the pi pulse hits, you're not doing anything. Between the pi pulses, flipped relative to x, and then after the second pi pulse, you come back to x. Okay? So in this logic, we look at what happens to the dipolar, the homonuclear dipolar Hamilton. And for simplicity, I'm just going to write that as C1 comma C2. And when I do this, I'm just referring to the terms in the time dependent part. So remember that this is where the time dependence of the dipolar Hamiltonian is. That's where your cos omega RT and cos 2 omega RT are embedded, multiplied by 2I1Z, I2Z. Well, as we said, this was something like this. Right? This Hamiltonian can be simplified because I1 dot I2 in Cartesian becomes XX, YY, and ZZ. Then you subtract out the ZZ term to get this. Okay. Does this make sense so far? I'm going to do a little trick which is useful for handling these rotations, especially because we're going to do a lot of rotation around Z. And because X rotation around Z gives you cos and then sine of Y and so on and so forth, then I want operators that are kind of like eigen operators of rotation around. So we had in class talked about I plus and I minus, plus being X plus IY, I minus the IX minus IIY. If this is what, and you wanted to convert I1x, I2x plus I1y, I2y into these raising and lowering or shift basis operators, you could do that at home. I highly recommend that because it becomes very useful for this sort of exercise. You get C1, C2, 2I1z, I2z minus half, I1 plus, I2 minus, I1 minus, I2 plus. Not doing the calculation here, but I strongly recommend that you go back and look at that. And this is what you will get. So when we actually solve this problem, we handle the Hamiltonian in this manner because the properties of I1 plus and I2 minus. But before we do that, let's just take this Hamiltonian by itself. What happens to it when you slam, when you've taken a delta function 180 pulse and you look at the Hamiltonian before and after? You have one answer, nothing. Other answers? I've just done this operation. So t less than half the rotation period is you're doing nothing. And for this duration, this is your operation. Rotate to 180 around x. And what happens to this Hamiltonian in that toggling frame? Toggling because toggling with plus x and minus x. What is the other side of the toggling frame? What does it look like? Remember, z goes to minus z, y goes to minus y, x will remain where it is for a 180 rotation around x. So what happens? Same. You get back the same thing because I1z, I2z becomes I1z, I1y, I2y becomes I1y. So the spin part of the Hamiltonian is unchanged by this 180 pulse. And obviously, I haven't done anything to these terms, which are the mechanical rotation of the sample at the magic end. Then the average Hamiltonian for one rotation period is, do we all agree? Just trying to follow. My logic so far is flawed, and it has a flaw which I'll come to hopefully next time. But if I show you follow my logic, which leads you to say that, in my toggling frame, which is defined like this, RF T, HD, T, for 0 less than T less than tau R, for the entire rotation period, I just get the same thing over and over again. And I just said this averages to 0 over a rotation period. Do you follow me so far? This was the interaction frame Hamiltonian. The interaction frame Hamiltonian. This then is average, which is this integral, is 0. Does this make sense? All our higher order terms in the Magnus expansion or higher order average integral, they will also be 0 because this first order term is necessarily 0. That is because, if that was the case, this false program would not work for homonuclear magnetization transfer. It does work. And the reason that it does work is because it neglected the effect of the isotropic chemical shift Hamiltonian, which interacts with the homonuclear dipole. Because we are out of time today, next week or whenever we come back, we will do a doubly toggling frame. The first toggling frame will be relative to the chemical shift, and the second toggling frame relative to the RF Hamiltonian. That will produce a non-zero average Hamiltonian, which can allow for homonuclear magnetization transfer. Any questions? It was a bit of a speed run. But this is how you would approach average Hamiltonian theory with delta function pi pulses for a Hamiltonian by itself. So this works, for example, perfectly well for heteronuclear dipolar couplings. And you can think of the equivalent pulse program. You can look in the literature for what the equivalent pulse program is, and you can apply this logic and check for yourself that applying 185 pulses at half rotation periods does bring back the dipolar count. But when you do it to the homonuclear coupling, it does not work by itself unless you account for other mechanisms. No questions. We'll see you next week.
risk. Our 230 been by the way. The gravity takes. We heard that. Oh, yeah. Oh.